Welcome to this plenary session. It's my honor and pleasure to introduce Professor张益唐. Kronecker once said that God created the integers and all else are work of man. The prime numbers are building blocks of the integers, and the twin prime conjecture is so natural and so beautiful that it must be the conjecture of the God. So, in the following, Professor张益唐is going to talk about his decisive progress towards the twin prime conjecture. You can read his story on the internet, in magazines, in newspapers. So for his story, he needs no introduction. Let's welcome Professor Zhang.
Thank you very much. So let's start with the primes. I'm not going to repeat the that should be the first time for me to use this. So if I forgot something like this, just mention to me. Okay, let me know. So we start with such a way, assume P is a prime number. And we introduce a set. We say it is admissible in such a way. In our notation, we say H is a finite set, like this, where the small h, H1 till H sub k, are first, they are distinct. And non-negative images. We say the definition. We say such a set of non-negative images H, capital H, is admissible. That means for any prime P, there is an image, we say H, such that each of these numbers, n plus H1, n plus H2, till n plus HK, Sorry, we say that each of these numbers is not divisible by the prime P. That's our definition of the so-called admissible set, capital H. Let's see some examples. We say that H. Actually, this corresponds to the prime, the twin prime conjecture, or maybe something more. We may verify, it's not difficult, that they are admissible. But how about something else? We say maybe some other sets may not be admissible. We say, but let's see this set, 0, 2, 4 is not. Why? We may verify it. I'm not going to give the proofs. Let's try the P equal to 3. Can we find some n such that the n plus 0, n plus 2, n plus 4 are, each of them is not divisible by 3? No. Now I would like to mention a a stronger conjecture. That should be very important in history, the so-called Hardy-Littlewood conjecture. There are several Hardy-Littlewood conjectures. This is just one. We say that. Conjecture. We say if H is admissible, then that should be there exist infinitely many positive integers, let's just say n, such that each of these k numbers, n plus h sub 1 till n plus h sub 2, is a prime. That's a Hardy-Littlewood conjecture. And let's see one special case. We just say, the k equal to 2, and the very simple case, the h is this set 0, 2. That is just twin primes. Conjecture is the same. But of course, the general statement of the Hardy-Littlewood conjecture is much stronger. Till now, of course, we are far from being able to prove something like this. Let me state my result, but this result currently may not be the best theory. We say assume H is admissible with a constraint which is, we say this depends on the number of the number of the integers in this set, which is k. 3.5 million. But now I say this result may not be the best. Or on the website you may find some improvement. But till now, what should be the smallest value for the k? That's it's possible. I don't know. So such a condition. Then there exist infinitely many positive integer n such that the set for each n we say n plus h sub 1, n plus h sub 2. This set contains at least 2 primes. That's my major result. Here, let me say, we say at least 2. But maybe should be at least 3 or at least 4. That should be much harder. Till now, we don't know how to prove it. But if we say contains at least 1, that is trivial, right? For that, I may not have said something more to say. At least 2, it is significant. So then we say the gaps between the consecutive, and we give a bound something like the 70 million something. Now it is much smaller. I don't know what's the precise value. Now I would like to say, as we know, even we say the subject of number theory is divided into many parts, like analytic number theory, algebraic number theory, and arithmetic geometry, varies. But what I like to say is the analytic number theory has something very special. It may not be too special to me, but maybe we find that lots of problems are reduced into evaluating or estimating a certain sums, very complicated. So the notation, if we write down the expression, it could be very complicated. But why we can do something like this? We say the treatment of our problem is like this. Let's we introduce something more, is a large number. In our application, we just assume x goes to infinity. And a standard notation for the convention is like this. We say n is similar to x. Maybe we say similar. Just means n is between the x and the 2x. There's something like this. Then we try to introduce a function. I say it is theta. We say theta m. That is just a characteristic function of primes. Thus, we say if it is equal to either 1 or 0, if m is a prime. If m is not a prime, is 0. So we consider the sum, then x is arbitrarily large, it goes to infinity. So we compare. Two sums, which is the so-called S1, it is just equal to, I will introduce something else. The Fn, I didn't mention it, what means that. But I will say, we will come back. Here also, let me introduce something inside. That is J from 0 to K theta. Till now, we have only one constraint on the function f of n. It may depend on x, depend on everything, but only one thing is, I say with must be non-negative condition. Then you say, we may ask, what means that? Then let's compare. That is, let's come to here.
Maybe you can put our other blackboard down.
If with a choice of the function f of n, we can prove S1 is strictly greater than S, or S2 is strictly greater than S1. Then let's see here. The summation, the same as that. Here when we say it is 1, here it is that. That's a sum. But for the non-negative f of n, then this implies, we compare these. It's strictly greater than 1. For some n is in this interval. And now x is arbitrary. We just say we assume for nx sufficiently large, we just consider it goes to infinity. For any large x, always we have some n such that this implies what? I may not say. We say at least 2 primes in this set. This is why also I would like to mention it should be a very general idea in analytic number theory. Reduce a problem like involving the prime numbers distribution to evaluating or estimating and or comparing certain sums. Now the next question. How can we choose? I put it here, only the non-active function f of n. Yeah, then we say in a Chinese word, it could be like we are seeking a needle under the ocean. Because there are too many non-negative functions. So let's see. Now we may use this board. Could you hear me? Sometimes I might. I just say how to choose. We have only one constraint. Let's try something like this. Let's try something very simple. So try. We say f of n is always equal to 1. Yeah, this is very simple to also. Then we find that the s of 1 is approximately just equal to x. This is just 1. But this s of 2, by the prime number theory, it is, here we say k is a constant. The major part, here we just say the major part, is approximately is equal to this. So of course this choice does not satisfy what we need, right? The S2 is much smaller. And also we may say some other, we may not have enough time to give some other strange choices. And there are some other choices. Oh, let's say, we say f of n is equal to 1 if. But you may say that actually is a very stupid choice. If from here less than right? Yeah, we say, this choice should work, but we do not know a function like such defined in this way, is it identically equal to 0? It could be identically equal to 0, then that still does not work. Now, I would like to mention something that is very, very long historical process. Basically, that comes from Selberg's seed, the basic one. Then, so which part we may address? Let's continue. In the history, a lot of problems in the sieve method are similar to that. Also, we needed to find a function. In general, it should be non-negative. But for some certain n, it should be not very close to 0. It could be equal to 1, larger than 0 or something. Then the Selberg's idea is, first we assume f of n is the square of another real function. We only assume the number n, this is another function that takes the real value. Then the non-negative condition is always correct. Then the question is reduced. What is the number of n? How can we choose this? Here, that could be too long time. I just mentioned something like this. We know the k is the constant here, we already give it. That was the major contribution from Stone, Pintz, Udrim. Should be like this. We will say this is GPY. They found a very appropriate choice of the form of the number n. That is, it's very complicated, could be, but we have to write down it. That is the summation over the divisors, positive divisors of the capital P of n. I will say something more about that. But we make an restriction. Here we are given a factor which is a number mu d. Maybe too many things. I will explain it. And for normalization, we put an constant factor here. Capital over D. Then for this logarithm, we have a constant of power. And this equal to this is D is less than capital D. O no, just that's it, just like this. And here, let's see, capital P is a polynomial that takes the product form. Depending on the set H, and here L is an image, positive image. It is also a constant. Depending on K, we may choose it flexibly. And the mu D is, I'm not going to repeat the definition, Mobius function. And the capital D is a power of it with the constant exponent of the given larger parameter x, which is C. Here C is a constant. This also comes from the basic idea of Selberg in the sieve method or something like this. We may, but later on I may come back to say something more about this. But we already know it is so complicated, right? Now, with such a choice, what should be the results on our sum S1 and S2? That is, we say results on S1 and S2. That is, S1 approximately equal to a constant, we say it is T1, something like this. X multiplied by the natural log of x with the coefficient it is k plus 2l. And S2 approximately equal to another constant. We say T2 star. Also here it is x, the natural log of x. But now we know S2, it itself contains the characteristic function of the primes. So in the evaluation of S2, the arrow term comes to play. That will be the most crucial part. I just say, let me use the standard notation, O of E star. Here, we say the S1 star, S2 star. They are constant. But these constants depends on many things, many other constants. We may say the K, actually it is not only K, the set. This already contains K. We have the K elements in this set, and also another constant L, and the constant C, maybe something else. And E star, here temporarily, let me just say it equal to the arrow. Where this arrow mainly comes from something later on we may mention. So now the question is, we need to, in order that the S2 is greater than S1, we need the coefficients in the main terms. This is greater than that. Meanwhile, we should be able to efficiently bound this arrow term. If we cannot show this arrow term is small in comparison with the major term, still we are unable to handle it. That's a major problem. Now the result